Okay, these are notes on 1-7, inverse relations and functions. This is the last section in Chapter 1. So as we study inverse functions, inverse relations are going to exist if and only if one relation, get a green highlighter here, one relation contains AB wherever the other relation contains BA. So when you have inverse relationships, your x and y values are going to switch positions. When a relation is expressed as an equation, the inverse relation can be found by, right here, interchanging the independent and dependent variables, otherwise known as your x variable and your y variable. So let's look at this example below. We have a parabola, x squared minus 4, a quadratic going through the y-axis at -4. Okay, so that's the relation described right here. So these would be the ordered pairs that go with that relation. -3, 5, -2, 0, -1, -3, so on and so forth. If we look at the inverse of this relationship, we would have x equaling y squared minus 4, or y squared equaling x plus 4. So what happens in an inverse relationship, before we talk about solving it algebraically to find the inverse, we look at the ordered pairs. Whereas I had -3, 5 in the original relation, in the inverse relation, I have 5, -3. They've switched places. When I had -2, 0, I now have 0, -2. -1, -3 becomes -3, -1. So all of these are going to just reverse in order. And so this can be very helpful when we have to graph an inverse. If we know the ordered pairs of the original, to graph the inverse, all we need to do is reverse the ordered pairs and plot those points. So we don't always have to find the equation. Okay, so if I plot the inverse, 5, -3, 5, -3 is right here, 0, -2, -3, -1, we see that it flips this parabola onto its side. Okay, so you probably remember that inverse relationships, this red dotted line, are always symmetric over the line y equals x. So that means we can take that quadratic, flip it over or reflect it over that line y equals x, and we have the inverse. Okay, as we continue on, as you can see, these inverse relations are reflections of each other in the line y equals x, which we just talked about. This is true for the graphs of all relations and their inverses. They are always going to be symmetric over the line y equals x. But in pre-cal, we study functions. So we are specifically looking at functions that have inverse relations that would also be functions. So in other words, we want the original to pass the vertical line test, and we want the inverse to pass the vertical line test. So if the inverse relation of a function f is also a function, then we're going to call it the inverse function of f, and the notation is written like this, with an f and then a little negative exponent, little -1 as the exponent. This represents the inverse function of f. Okay, so what's important to note is that not all functions have inverses. When we look at the above function, the original parabola is a function. It passes the vertical line test. But if you look at the inverse, it does not pass the vertical line test. If we go up here and draw a vertical line, it's going to touch it in two places, in several areas. So it has an inverse, but the inverse is not a function. And that's going to be key as we go forward in this course. Now, if you don't want to have to graph the inverse to know whether or not it's a function, we're going to look at the original graph. So if we look at the original graph, and I'm going to go erase all the things that I've put on there so we can just look at the clean original. If I look at the original graph, how can I know whether or not the inverse will be a function? We have a different test, and you probably remember it from Algebra 2, the horizontal line test. The horizontal line test tells us about the inverse. So in this gray box, here's what it says. A function f of x has an inverse function if and only if each horizontal line intersects the graph of the original function in at most one point. So if you look back at the parabola, at the quadratic up top, if I draw a horizontal line, it's going to touch it in two places. So that would tell me that my inverse function, or my inverse would not be a function. Okay, so let's look at a couple of examples. We want to graph each function using a graphing calculator. So if you want to pause this video so that you can put this on your calculator, I would really recommend that you do that so that you are okay with doing this. To find the absolute value bars for this first one, you are going to go into math and you'll find one of the options that says ABS, and that'll stand for absolute value. So as we look at these functions, the first one being absolute value of x minus 1, we're going to apply the horizontal line test and determine whether or not its inverse function exists. It will have an inverse, but whether or not the inverse is a function is what we're after. So as we look at this graph, it's the absolute value of x minus 1. So from our past experience in graphing these absolute values, I know it's going to be a V shape, but this minus 1 will shift that absolute value parent function 1 unit to the right. So I'm going to have a vertex here at 1, 0. And there's the absolute value of x minus 1. So this is definitely a function, but is f inverse a function? That's the question. Here's where we can use the horizontal line test. So when I draw a horizontal line, I touch it in two places, so this fails the horizontal line test. So is f inverse of x a function? No. If I were to reflect that over the line y equals x, I know that the ordered pair is reversed, so whereas I have this ordered pair 1, 0, the inverse would have 0, 1, and it would maybe look something like this, and the inverse would fail the vertical line test. Okay, let's look at example B. I would suggest that you stop the video and try example B on your own and see if you can answer this question. Okay, as we look at g of x equaling 4 over x, the parent function of this would be 1 over x. And all that really happens here is we have an a value of 4, so that's really 4 times 1 over x, which simply is going to make it stretch or compress. Make it stretch, actually. So all we need to do, if we just want to see if the inverse is a function or not, we can just sketch this graph. It's going to look something like that. If you used your calculator, that's okay too. So if we want to know whether this g inverse of x is a function, we're going to look at g of x. And as you can see, anywhere I draw a horizontal line, it only touches once. So this passes the horizontal line test. So if I were to reflect over the line y equals x, yes, the inverse would be a function. Okay, now that was good for looking at graphs, horizontal line test, ordered pairs. Now let's look at the algebra. Finding inverse functions. If a function passes the horizontal line test, then it is said to be, and you've heard this term before I'm sure, 1 to 1. And what this means is that no x value is matched with more than one y value, and no y value is matched with more than one x value. So essentially, the x's don't share and the y's don't share. Nothing will be repeated. Every x has one y, every y has one x. So if we're looking at the equation, the first thing we're going to do, actually, if we look at the graph and we know what the graph looks like, we're going to do the horizontal line test. So to find an inverse function, the horizontal line test will tell us whether or not the inverse is even a function. And if it's not going to be a function, we're done at this step. But if it passes the horizontal line test, then we're going to keep going. So the next step, since you are often given, right now in pre-cal, everything we have is in function notation. So we're first going to, or secondly, we're going to replace f of x with y, and then we are going to switch x and y. Oops. Okay. Now, I want to put a little side note in here. The exception is when you have a formula. So if you have the formula for the area of a triangle or a circle, or you have the formula for converting Fahrenheit to Celsius, if you need to find the inverse, you do not switch x and y or the variables. You will simply solve for the other variable. So when you're dealing with a formula, you just solve for another variable. If there's only two, you just solve for the other one. If there's more than two, then you would solve for the variable in question that you're asked to solve for. Okay, so that's a little exception when we're finding inverses. So we've replaced f of x with y, we've switched x and y, and then the next step is going to be to solve for y. And once we do that, we will replace y with the correct notation now that we're in pre-cal, which will be f inverse of x. If we started out with f of x, now we have f inverse of x. Okay, and then the last step, we have to do this in pre-cal, is to state the domain restrictions. Anything that we're not allowed to plug in, we need to make sure we have a little disclaimer on that. Okay, so let's put this into practice. Example 2, determine whether f has an inverse. And then if it does, find the inverse function and state any restrictions on its domain. So as I look at this rational function, again, you can graph this on a graphing calculator, or you may remember what this looks like. This has a horizontal asymptote at 1 because the degrees are the same, and it's the ratio of the leading coefficients. And it has a vertical asymptote at -2. -2 is where the function would be undefined. So I have some asymptotes there. And this graph is going to look like this. Okay? So it passes the horizontal line test. So yes, it has a function, or an inverse that is a function. Yes. Inverse is a function. It passes the horizontal line test. Okay, so now that we know that, We're going to replace, actually, let's do this first. We need to look at restrictions right now. As you look at the domain for this, you would not be allowed to plug in. If we look at domain and range, this is one thing I want to point out with this problem. Just like the ordered pairs reverse, xy becomes yx in an inverse, you might remember that the domain values and the range values also switch places. So as you look at the domain for this, the domain would be from negative infinity up to -2, and then from -2 to infinity. And the range values, looking at it vertically, the range values would be from negative infinity to +1, and then from 1 to infinity. So those are part of our original. Okay, so I'm going to circle this and make this all a little bit smaller and give me some more room. Okay, kind of move this out of the way. All right, so now we're going to replace f of x with y. And I'm going to switch x and y. So now I'm going to write my equation as x equaling y minus 1 over y plus 2. So I have to solve for y, and I have it in two different places. I'm going to proceed like normal. Think about x being over 1 and just solve it like a proportion. So I'm going to multiply x times y plus 2, which will give me x times the quantity y plus 2. And then when I multiply in the other direction, 1 times y minus 1, which is just y minus 1. So to get y by itself, what I want to do here, I'm going to distribute the x, xy, plus 2x equals y minus 1. So now, to solve for y, to get y by itself, what I'm going to do here, and pay close attention, I'm going to get everything with a y on one side and everything that doesn't have a y on the other side. So I'm going to subtract y from both sides and subtract 2x from both sides. So I would have xy minus y equals -1 minus 2x. Let's factor out a y, and I'm left with y times x minus 1 equal to, and I can rewrite this, -2x minus 1. So to get y by itself, I'm going to divide both sides by x minus 1. And now y is equal to -2x minus 1 all over x minus 1. So when you look at this, now that we've solved for this, I'm going to go one step further. I'm going to replace y with f inverse again. So f inverse of x is equal to -2x minus 1 over x minus 1. And my new domain is what my old range was. Remember, my old range for the original f of x was -infinity to 1 and 1 to infinity. So that is now going to become my domain, and we can see that's true right there. I'm not allowed to have 1 in the denominator. So domain is -infinity to 1 and 1 to infinity. Okay, so that's letter A. Took up quite a bit of room on that. I'm going to have to shrink that down quite a bit if I can. Okay. All right. Okay, let's look at letter B. And if you want to try this one before you watch me do it, that would be great. Okay. First of all, we're going to look at f of x equaling the square root of x minus 4 and think about what its graph looks like. So this is a square root function, and that minus 4 moves it 4 to the right. So I'm going to move 4 units to the right, and there's my square root function. So this does have an inverse. Yes, has an inverse. That is a function. And the reason is because it passes the horizontal line test. Okay, so now that we know that it will pass the horizontal line test, the inverse will be a function, we're going to keep going. So I'm going to replace y with f of x, or replace f of x with y, equal to the square root of x minus 4. And as I look at this original, and I can look at the graph, or I can look at the equation, I can see that my domain has to be from 4, including 4, to infinity. My range is going to be from 0 to infinity. So I would expect that when I find the inverse, those are going to swap places. Okay, so I'm going to now swap x and y. X is going to equal the square root of y minus 4. To solve for y, I'm going to square both sides, and I get x squared equal to just a y minus 4. I'm going to add 4. So I get x squared plus 4 equal to y. And I'm going to replace that with f of x, or f inverse of x. So f inverse of x is x squared plus 4. So if I go over to this graph and I look at this, if the domain of the original was from 4 to infinity, then that will be the range of my inverse. So my range is going to start at 4 and go up. And if the range of my original was 0 to infinity, the range of my inverse will be, the domain of my inverse will be 0 to infinity. So even though this would be a full-blown quadratic, both sides, we really have to restrict that domain now because of what it came from, and the domain would be 0 to infinity. And again, that was what the range was in the original. That's now the domain in the inverse. Okay, so that takes us through inverses and determining whether or not the inverses will be functions and how to find them, how to see them graphically. Now we're going to use composition of functions to prove that two functions would be inverses. And this is something you definitely have done before in Algebra 2, but let's go over this again. Again, these equations are oftentimes at a higher level than maybe the equations you dealt with in Algebra 2. So you still need to be just as sharp on these concepts. Okay, compositions of inverse functions. Two functions, f and g, are inverses if and only if this happens. If I do the composition this way, f of g of x, and I get x, and then I do the composition the other way, g of f of x, and I get x. If that happens, where doing the composition both ways gives me just an x, then that proves that they are inverses. Okay, so we're going to try example 3. So as I look at example 3, I have f of x and g of x. F of x being 6 over x minus 4. G of x is 6 over x plus 4. So I'm going to do f of g of x and see what I get. And then over here, I'm going to do g of f of x. And these can look pretty scary when you're substituting, but just kind of press through, cling to those algebra rules. And if they are inverses, it's going to turn out really nice. Nice things will happen and cancel. So f of g of x is my 6 over x plus 4. So I'm going to go to f, and where I see an x, I'm going to plug in this entire quantity. So I look at f, which is 6 over x minus 4, and I'm going to have 6 over, now I have this entire thing, 6 over x plus 4, but then minus 4. So as I simplify this, in the bottom, 4 minus 4 cancels out. So I'm left with 6 divided by 6 over x. Well, I know that fractions are division, so I can think of this as 6 over 1 divided by 6 over x, or change it to multiplication of the reciprocal, x over 6. And what happens is the 6's cancel, and I'm left with just x. So we're halfway there. This is what I want, but I have to make it has to happen for the other composition as well. So as I look at the other one, g of f of x is 6 over x minus 4. I'm going to go to g of x, and where I have an x, I'm going to plug in 6 over x minus 4. So let's see how this plays out. So I have 6 over x minus 4, 6 over x minus 4, and then plus 4. So I'm going to take care of this complex fraction first, break the division down. So again, just like we did in the previous example, this is like 6 over 1 times the reciprocal, x minus 4 over 6. And I'm still adding 4. Can't forget about that. So as I do my multiplication, the 6's are going to cancel, and I'm left with x minus 4 in the top and then plus 4. Those cancel, and I'm left with x. So when I did the composition both ways, the key is that I got x, and so this tells me that f of x and g of x are inverses. And the composition is what proves that. Okay, so the last page, we're going to look at a graph. This first example, we're going to look at the graph, and we're going to use the graph to sketch f inverse on the same coordinate plane. We can see that f of x passes the horizontal line test, so f of x, or f inverse of x, will definitely be a function as well. Okay, so as I look at f of x, I see that I have points on that graph. Some nice points that I have are 1, 2, I have 0, 1, and I have negative 1, 0. So as I look to graph the second point, or the second line, the inverse, I should have points switch places. So 1, 2 is now going to become the point 2, 1 right here. 0, 1 becomes 1, 0. And negative 1, 0 becomes 0, negative 1. Okay, so this is not super easy to draw because right now those 3 points make me want to just draw a line. However, I know that it has to have the same shape, and I know that they are reflected over the line y equals x. So as I draw this, I'm going to try to do this. It's okay. Not great, but yes, that should be, let's see, 2, 1, 1, 0, okay. All right, so pretty close estimate. Again, you know my drawing's not very good, so just bear with me on that. All right, and that's example 4. We're going to end this lesson with a word problem, of course, relating back to everything we've talked about. Okay, so let's read this. Caitlin earns $8 an hour, and she works at least 40 hours a week. Let me highlight some of this stuff. She makes $8 an hour, 40 hours a week. Her overtime pay is 1.5 times her regular hourly rate for any time over 40 hours. So her total earnings, f of x, for a week in which she works x hours is given by this. So this right here represents total earnings based on hours. Okay. So, in letter A, explain why the inverse function f inverse of x exists. Okay, so for it to exist, we would want the original to be a one-to-one function. So if we think about this in terms of this problem, we know that the number of hours she works, every amount of hours that she could put in, only has one amount of pay that goes with it, and vice versa. Every amount that she makes only goes with 1 hourly rate. Okay, so to write that down, we would just say, because each amount of hours has one rate of pay, and vice versa, the other way around. So this essentially represents a one-to-one function. Then it wants us to find f inverse of x. So this is not just a random xy equation. This is a formula for calculating earnings. So we are not going to switch to find f inverse of x. We're not going to switch x and y, or in this case, x and f of x. We're going to just solve for the other one. Now I'm going to go ahead and rewrite this so maybe we can understand it better as we go. I'm going to let f of x represent earnings, and that is equal to 320 plus 12 times, and I'm going to call that x and h for hours, minus 40. Now to understand this question, if she works 40 hours, that's no overtime. So if you think of h as being 40, that's going to give me 0 in there. And so your base pay would just be $320 for that week for 40 hours. Now, it's only after you go over 40. So in other words, if you worked 42 hours, you would multiply or subtract 42 minus 40 to get 2 hours of overtime and multiply that by 12 and then add your base pay of $320 to that. So just to help you understand how that formula is working to get earnings. Okay, so I want to solve for hours. That's how I would find the inverse of this. The first thing I'm going to do, if I want to get to h, I'm going to subtract 320 from both sides. So earnings minus 320 is equal to 12 times hours minus 40. Then I'm going to divide by 12 the entire side. So I have h minus 40 equal to e minus 320 over 12, and I'm going to add 40. So I now have h equal to e minus 320 divided by 12 plus 40. So this is my inverse. So this is also the F inverse of x that they're referring to. So in question B, what do F inverse of x and x represent in the inverse function? So in the first one, I had earnings depending on hours. Now, this equation represents hours worked, as a function of earnings. Okay. All right, so being that this is a real-life application, let's talk about restrictions and reasonable domains. Letter C says, what restrictions, if any, should be placed on the domain of f of x and f inverse of x? Well, let's look at each of them and explain why. So f of x, let's talk about that first. So f of x was the original 320 plus 12 times x minus 40. So what could go into that function? In the original f of x, x represented my hours. So what could we plug in for hours? Well, a realistic domain would be at bare minimum 40 hours. Now, at the maximum, which maybe it's not as realistic, but a maximum would be to figure out how many total hours there are in a week. So if I come over here, 24 hours in a day times 7 days a week is 168 hours in a week. So there are that many hours in a week. So those would be the possible domain values to be able to be plugged in. Now for range, the way that we would find the range is we would go evaluate the highest and the lowest amount of earnings. Well, we already know that for 40 hours, that's your base pay of $320. So if you worked every single hour of the week and you plugged in 168 for those hours, I've done the math on this, you would have $1,856. So you could make $1,856. Realistically, not realistically, if you worked every single hour of the week. Okay. Now, F inverse. If you look at F inverse now we have a function where the x, where the x represents earnings. Earnings would be what gets plugged into the equation. So F inverse of x, to look at that domain, would now be you could earn anywhere from, or you could plug in any earning amount from 320, which is the base, all the way up to 1,856. Remember, when you're looking at inverses, domain and range switch places. My old range is my new domain for the inverse. And then my range, my output, is my hours. And the possible hours that I could have would be from 40 to 168. So they just completely swap places. Now, where it says explain, you can write that in your own words, kind of just what I talked about with the realistic expectations that it's a 40-hour week, and then we have 168 hours in a week, and then plugging those into the equation to figure out our maximum and our minimum earnings, potentially. Okay. Letter D, the last one to go with this. Find the number of hours. So we need H, that Caitlin worked if her earnings were $380. So I'm actually going to use the inverse, because that's where I have hours as an output and earnings as my input. So hours would equal 380 in earnings minus 320 divided by 12 plus 40. So how many hours does she have to work to make that much money? So 380 minus 320 gives me 60. Oh, that's a 40, sorry. Gives me 60 divided by 12 plus 40. 60 divided by 12 is 5 plus 40. So she would have to work 45 hours if her earnings were $380. Okay, so that's the end of chapter 1. If you have any questions, let me know. Need to stop the recording.